In this video, we will learn about internal forces, topic 7.1 from chapter 7. This is the only topic 7.1 that we will cover in this course from chapter 7. Internal forces. Today's objective is to understand the concept of internal forces and use the method of sections for determining internal forces in two-dimension load cases. So in structure, typically until now we have never considered the internal forces except the method of section, because internal forces, they have equal magnitude but the opposite direction. So for the purpose of overall external force analysis, they do not play any important role. However, regarding the strength of the component, they play important role. For example, this like metal rods, when we take the cross section, they are subjected to load within the inside of them, and they can actually fail because of that loading condition if the load is more than the capacity or strength of this material. So look at this example, that when a metal rod is, this specimen is being pulled in the tensile load, then internally it's subjected to stresses. So this color indicates the intensity of the stress inside the member, and at some point when it's more than the strength of the material, it fails. So this type of failure is called tensile failure. And the force that's within the member perpendicular to the cross section is called the normal force. There is another type of internal load is called bending moment. So when a load is being applied to a beam which is being supported, then because of, and if the load is more than the capacity of the beam itself, then the beam will fail because of bending. So it will just bend and break. So this type of failure is called bending failure, and that internal load is called bending moment. There is third type of internal load that we consider here is shear failure. So in this case of these two plates are being joined by means of this fastener here, and when the plates are being pulled in the opposite direction, then the bolt fails parallel to the cross section, and this type of failure is called shear failure, and that type of force is called shear force. So now all three internal forces in one diagram. So normal force here, perpendicular to the cross section. Bending moment is because of the bending load, and shear failure is parallel to the cross section. So we use letter N to define the normal force, we use V to define shear force, and we use M to define bending moment. And here are some example of the mechanical properties of the material, 6061 aluminum alloy, and its strength is given. So typically when we calculate the internal load, we divide that load by area, and that gives the value of stress within the member. So stress is equal to load divided by area, where load is the internal load. And if that number is more than this number strength, then that's not a good sign, because our component is subjected to stress which it cannot handle, and it will fail in practical application. So this is what engineers do. So they calculate the internal load, divide it by area, and calculate the stress, and make sure that the stress is within the limit. If it is not within the limit, then extra supporting members are required to be added. So in multi-force member, the member is generally subjected to an internal normal force, shear force, and bending moment, all of them. So the correct answer is all of the above. In mechanics, the force component V acting tangent to and along the face of the surface is called, so this V is called shear force. So in this diagram here, N is perpendicular to cross section at C, so it's called normal force. V is tangent to the cross section, so it's called shear force, and M is bending moment at C. Applications. So beams are structural members designed to support loads applied perpendicular to their axis. Beams can be used to support the span of bridges. They are often thicker at the support than at the center of span. So you can see that this is where the beams are much thicker compared to the center, which is thinner here. Why are the beams tapered? Internal forces are important in making such a design decision. In this lesson, you will learn about these forces and how to determine them. Another application is look at this billboard sign, a rectangular billboard. So a fixed column supports this billboards. Usually such columns are thicker at the base or wider at the base compared to top. And why is it so? Because it results in bending moment because of the weight of the billboard, and the bending moment is maximum at the joint where it's being supported or attached to the ground. So in order to give more strength to this entire like vertical column, it's made wider or thicker at the base. Another example is look at this Burj Khalifa building and see the structure. It's more like a triangular shaped structure where it's much wider at the base and much narrower at the top. What if the engineers designed this other way, narrower at the base and wider at the top? It would have not survived because maximum bending moment will be here at this point, and this point is very narrow, so it will not have strength enough to support the building. Another application, soft crane is used to lift heavy load, and this extra piece is added here to the frame, is welded to the frame to give the reinforcement to support the bending load. So this is all because of the internal forces. So the design of any structural member requires finding the forces acting within the members to make sure that the material can resist those loads. For example, in this case, we would like to know the internal stresses or forces at B. So then how can we do that? So first we need to determine the support reaction. So we will calculate AY and BY. Then the next step is we take the cross section that passes through B and keep the left side of the cross section and expose the internal loads such as normal force at B, shear force at B, and bending moment at B. And these are called internal forces acting at B. And then we can consider this as like a standalone problem and apply equations of equilibrium to solve for these three unknowns. So in two-dimensional cases, typical internal loads are normal, which is perpendicular to the cross section, shear, which is parallel to the cross section, and bending moment, which is shown here. And when we expose that member, like cut the member and expose internal forces, they are equal and opposite magnitude on both sides of the section. So for the left side, if the normal force is coming out, then for the right section also it's coming out. If shear is going down, then shear is going up on the other side of the section. Same goes for the bending moment. This is counterclockwise and this is clockwise. That means if we bring this together and join them, this internal forces cancel out. So this normal and this normal will cancel out. Shear and shear will result in net zero force inside the member, and bending moments are also cancelled out. So the loads on the left and right sides of the section at B are equal and opposite in equal in magnitude but opposite in direction. This is because when the two sides are reconnected, the net loads are zero at the section, and that's why the system is in equilibrium. So steps for problem solving: take an imaginary cut at the place where you need to determine the internal forces, and then decide which side of the section will be easier to analyze. If required, calculate the support reactions. Name internal forces as N, V, and M, so normal, shear, and bending moment, and apply equations of equilibrium and solve for the unknown internal loads. Okay, in the next video, we will look at one example. Thank you.